Road to Olympiad.
Welcome to RTO. Consider the following problem. Let px equal to an x to the power of n plus an minus 1 x to the power of n minus 1 plus an minus 2 x to the power of n minus 2 until a0 be a polynomial with integer coefficients such that p2 and p3 are both multiple of 6. Show that p5 is also a multiple of 6. Normally, if both a and b are multiple of a certain number, the sum is also a multiple of that number. But is it really true for polynomials? Well, it is true under certain conditions. Today, we will be proving one specific case for that statements. Pause the video if you like to give this problem a try, and when you are ready, keep watching to learn how to solve it. To solve these problems, we start by noticing that by substituting x is equal to 2 into the polynomial, we have p2 is equal to 2 to the power of n an plus 2 to the power of n minus 1 an minus 1 plus 2 to the power of n minus 2 an minus 2 until a0, which is divisible by 6. This implies that p2 is also divisible by 2. But since every term except the last term of p2 is obviously divisible by 2, this implies that the last term, a0, must be divisible by 2 as well. By the similar argument, we can substitute x is equal to 3 into the polynomial and comes out with a similar conclusion that a0 must be divisible by 3 as well. Combining the fact that a0 is divisible by both 2 and 3, it must be divisible by 6. Now consider p5, which is equal to 5 to the power of n an plus 5 to the power of n minus 1 an minus 1 plus 5 to the power of n minus 2 an minus 2 until a0, where we can rewrite each of the 5 as 3 plus 2 and expand each of the 3 plus 2 to the power of n by using the binomial theorems to obtain this one. Now here, notice that each term in each of the expansions, except for the first and the last term, consists of factor 2 and 3, and thus they are multiple of 6. Therefore, by taking congruent modulus 6, we can write p5 simply as 3 to the power of n plus 3 to the power of n minus 1 an minus 1 plus 3 to the power of n minus 2 an minus 2 until 3a1 plus a0 plus 2 to the power of n plus 2 to the power of n minus 1 an minus 1 plus 2 to the power of n minus 2 an minus 2 until 2a1. Recall that the sum of 3 to the power of n until a0 is simply p3 we obtained just now, which is also a multiple of 6. So we have this expression simply equal to the sum of 2 to the power of n until 2a1 congruent modulus 6. And these expressions remain the same if we add in an extra a0 minus a0. But with these extra terms, we notice that the sum of 2 to the power of n until a0 is equal to p2, which is a multiple of 6. And it's different with a0, which is also found to be a multiple of 6 just now, must be equal to 0, congruent modulus 6. Which conclude that p5 is a multiple of 6. And this marks the end of our solutions. Post in the comment below if you have any thoughts on the video, and if you haven't subscribed yet, consider subscribing. This will really help us out. Anyway, see you in the next video. Thank you.